All right, ladies and gentlemen, welcome back to physics class. We are going to talk about Newton's laws, and we're going to do some problems with Newton's laws. And so, this poor little guy, you'll understand in a little while. Isn't he cute? I feel so sorry for him. All right, so no friction. This would be what happened. He'd just like go exactly into the heaven forbid when the car stopped. All right, Isaac Newton. He gets all the credit for this, okay? He is the one who came up with the three laws, did a lot of investigating, did some things with apples falling out of the tree. So, really cool stuff. First law of motion says if no net force acts on it, a body at rest is going to remain at rest. And a body in motion is going to remain in motion at a constant speed and in a straight line. So really, this law is the law of doing what you are doing. Again, the key part is the words right here that say no net force. If there's no net force, then all the forces that do exist are balanced. Everything's at equilibrium. So objects are going to keep on doing what they're doing. All right, mass and inertia. Mass, remember, is just how much of particles exist in an object. The property that a body has of resisting any change to what it's doing is called inertia. And the inertia of a body is related to the amount of matter it contains. The quantitative measure of inertia is mass. What do you think about as a football player? You don't see a lot of, in the professionals, you don't see a lot of defensive linemen that are very small. And you don't see a lot of offensive linemen that are very small. And the point of that is that once they, probably the offensive line's a better example, but once they're set, and if they're a big guy, then it's kind of hard to move them because they have more mass. And the more mass you have, the more inertia you have. Mass will always be measured in kilograms, okay? So mass is the equivalent to talking about inertia. If we talk about 18-wheelers coming to a stop versus a VW Bug coming to a stop, they have very different mass values. So therefore, they change their motion really quickly as well. Okay? So one doesn't change its motion very well, and that would be the larger mass. The other has a lower inertia value because it has a lower mass. So Newton's second law is roughly yeah, I have all these great little thingies. I gotta move this so you can see my little thing. Y'all can read. I'm sorry. All right, it's late. We're gonna keep going. Second law of motion states that according to the second law of motion, the net force acting on a body is equal to the product of the mass and the acceleration of that body. The direction of the force is the same as the acceleration. That's the key part of this. Direction of the net force is the same as the acceleration. So, in equation form, this is on your formula chart, and it is F equals ma. Now, on your formula chart, though, what it looks like is it's our fourth formula on our formula chart, and it actually has A equals the summation of forces over mass. And notice it has a little arrow over the acceleration and the force, and that's because those are vector values, okay? So then it also goes on to say that the F of net over mass. Okay, so it's really just a different way of looking at an acceleration formula, which we've already had before as well. So the force of a hand accelerates the brick. How much it accelerates the brick depends on, 1, the mass of the brick, and 2, how much force you're applying. So I have a 60, and we're in our notes, guys, so I'm going to go through these problems with you because then I'm going to ask you to do some classwork with them. A 60-gram tennis ball approaches a racket at 15 meters per second. It's in contact with the racket for 0.005 seconds and then rebounds at 20 meters per second. Find the average force exerted by the racket. Okay, well, I'm given a mass value here, but this mass was given to me in grams. I'm going to have to convert that to kilograms. So I'm going to say for every 1,000 grams, I have 1 kilogram, which is going to give me 0.06 kilograms. Okay, and then I have an original velocity of 15 meters per second. And then I have a final velocity that is 20 meters per second, but the key is that it rebounds at that. So that means one of these has to be negative because one's going in this way and the other's coming out this way. So I'm going to make my 20 negative. All right. Then I know a time value of 0.005 seconds. Well, they want me to find force. Force equals mass times acceleration, right? Well, that's great, but I don't have acceleration. Is there a way that I could find acceleration? Hopefully you guys are like, yes. And then where could I find it? On the formula chart. Very good. Okay, so I could substitute F equals M times VF minus VO over T. That is the manipulated formula, the first formula on your formula chart, to solve for acceleration. So I can substitute that in. Then I can substitute the numbers in. Do that now. Okay. Pause this if needs to be paused. Actually, do it in your calculator and come up with an answer. I know you're just frantically writing and calculating, so I'm just waiting on you. It's all good. Hopefully we have an answer. Somebody has an answer. Yes. Hopefully more than one somebody has an answer. All right. So you should have gotten a negative 420 newtons away from the racket. It is negative because that would mean that it's moving away or it's rebounding out. And since I made the 20 negative, that's why that works that way. All good? Yay! All right, moving on. Next problem. The brakes of a 1,000 kilogram car exert 3,000 newtons. How long will it take the car to come to a stop from a velocity of 30 meters per second? Okay, I have a mass of 1,000 kilograms. I have a force of 3,000 newtons. And I have a velocity of originally 30 meters per second, and I have a final velocity of 0 meters per second because I want to come to a stop. And I'm looking for time. So again, I have my F equals MA, but I can substitute F equals M times VF minus VO over T. So another way to look at that would be F times T equals M times VF minus VO. And then I want to divide by my F to get my T by itself. So I can then say 1,000 kilograms multiplied by the negative 30 meters per second divided by the 3,000 newtons. I know you're writing this down. And you're calculating it because you have your calculators. And the magic number is... Oh, I didn't do it. Hold on a second. That's bad. I probably should have done that. 1,000 multiplied by negative 30 divided by 3,000. Hopefully you came up with an answer of a negative 10 seconds. Yay, us. Oh, we can have negative 10 seconds. How's that work? Oh, I know what it is. It was a braking force. What direction would a braking force go? It would go the opposite direction. So our force also needed to be a negative value right here. I forgot to tell you that. Sorry, guys. So if I had a negative force when I plug it in here, then when I have that negative value, that would make that a positive. Because we can't have negative time. Can't go back in time, people. So that would fix that for us. All right. Next question would be, how far will the car travel during this time? I bet we have one of our motion formulas that we could solve for this. We have our D equals VF squared minus VO squared over 2A. We don't actually have our acceleration though. So we could do our D equals V naught T plus 1/2 AT squared. But again, we're going to have to find our A value. So what is our acceleration value for this? We would have our A equals VF minus VO over T. So then we could say that we have our 0 minus 30 divided by 10 seconds. That's meters per second. So we have our acceleration of a negative 3 meters per second squared. And then we could solve for either one of those. Wouldn't matter which one we wanted to solve for, but we could solve for how far the car traveled during this time. And those answers should be 10 seconds and 150 meters. Looky there, we had to pull our motion formulas back in. All right. Next one, a 5 kilogram object is to be given an upward acceleration of 0.3 meters per second squared by a rope pulling straight upwards on it. What must the tension of the rope be? Okay, well, here's the thought process. We have our free body diagram. Let's draw this one first. We have 5 kilograms that we're going to put in the middle because when we have the mass, that's where I like to put the mass at. Then we're going to have a downward force of an F of G. And then we're also going to have an F of T pulling upwards. Okay? Now, when we find our F of G, we're going to have to say that's mass times gravity. So 5 kilograms times our 9.8 meters per second squared. So when we do that in our calculators, 9.8 times 5 gives me 49 newtons. That's just the downwards. We want to have an upwards acceleration rate, though, of 0.3 meters per second squared. So we need to figure out what net force is going to give us our mass times this acceleration value. Well, our mass is going to be 5 kilograms. Our acceleration value is 0.3 meters per second squared. So that is going to be 0.3 times 5. It's going to give me 1.5 newtons. Has to be my net force. Well, remember, I have an F of T minus my F of G because I want it to go upwards. That has to equal my net force. So that's why I made my F of T bigger, because I want the acceleration to go upwards. So my F of T has to be the bigger number if my acceleration is also going to be going that direction. So I could then say, well, plus F of G on this side. So I'll plus F of G on this side. So I'm going to do my 1.5 newtons plus my F of G, which I just found was 49 newtons earlier. So then I will add those and I get 50.5 newtons. And that would be my F of T value. Lots of little craziness there. And that would be upwards. All good? Hopefully everybody's understanding that. Yay! All right. My last one that I'm going to do today for you, I think, is going to be a 200 Newton wagon is to be pulled up a 30-degree incline with a constant speed. How large a force parallel to the incline is needed if friction is negligible? Okay, well, I've got an incline just like this, and this is a 30-degree angle. And actually, I'm going to stop here. I'm not doing this problem because I'm going to get into inclines when I get back. So I'm going to stop there. You guys are going to do a station activity. And if you don't do station activity, then you're going to do a worksheet. But you guys are now going to do a class activity that is dealing primarily with Newton's second law. So I'm going to skip past this one. And we're going to talk about Newton's third law really, really quick because it's really easy. This is funny. You know, it is. Gravity works. Physics is simple. All right. The third law of motion is really easy. When one body exerts a force on another body, the second body exerts exerts on the first an equal force and in the opposite direction. Key things here, you have to have two objects, two forces, equal and opposite. This object, I have a hammer, it is applying a force downwards, and the nail is applying a force upwards. They should be equal and opposite. So the third law applies when we have two different forces on two different objects. The action force of one object exerts on the other is equal to the reaction force of a second object on the first. Okay? So this is called the action-reaction law because, again, but it always is that the forces occur in pairs. Pairs of objects, pairs of forces. So the tire pushes on the road pushes on the tire. Two objects, two forces. The rocket pushes on the gas pushes on the rocket. Two objects, two forces. Okay, really simple. So you guys are now going to do, like I said, some station work. Have fun, work around the stations as quickly as you can. I think that you guys are going to end up working about, let's say, I don't know, I have 6 stations and you probably have about 30 minutes left. So let's just say we're going to spend 5 minutes at each station, do as many things as many questions as you can at that station. Okay, so you're going to be going to your star stations and working around the room. You're going to just write the title of each of the worksheets, and then you're going to roam around accordingly. Okay? Have fun. Be good.